Welcome back. Video 4 of 5 and a change of subject, probability and information theory. Every prediction a neural network makes is a probability, so this is the logic of the whole field. We'll build from coin tosses to random variables and distributions, master marginal, conditional and joint probability, meet expectation, variance and covariance and confront Bayes' rule, including a medical test example whose answer will genuinely shock you. We close with information theory, the mathematics inside the most used loss function in deep learning. Let's dive in. Welcome to part 2 of the unit probability and information theory. Let me motivate this with one sentence. A classifier never says CAT, it says CAT with probability 0.93. Every single prediction a neural network makes is a probability. If you can't reason about that number, you can't reason about deep learning. That's why this chapter exists. Our climb, we start gently with coin tosses and dice, random variables and sample spaces. We build up through probability distributions, binomial and Poisson. Then the three flavors of probability: marginal, conditional and joint. Then expectation, variance, covariance, the legendary Bayes' rule, including an example that will genuinely surprise you, and we land at information theory, mathematics behind the most used loss function in deep learning. Coins to cross entropy? Let's begin. First question: why does machine learning need probability at all? Here's the contrast. Most of computer science is deterministic. A programmer safely assumes the CPU executes every instruction flawlessly, the same way every time. Certainty is the default. Machine learning lives in the opposite world. It must always deal with uncertain quantities, noisy sensors, incomplete information, randomness in the data itself. The textbook gives probability to official jobs. In AI Job 1, the laws of probability tell us how systems should reason. We design algorithms to compute probabilistic expressions. Job 2, probability lets us analyze our systems to prove things about how they'll behave. Here's the picture to keep. A self-driving car never knows a pedestrian will cross. It estimates probability of crossing, 0.85 from noisy cameras, and decides to brake. Uncertainty isn't a bug to be fixed, it's the operating condition of intelligence. Like every branch of math, probability starts by defining its vocabulary very carefully. Word 1, the experiment. An experiment is any physical action or process that we observe, noting the result. Simple. But the interesting kind is the random experiment, which needs two conditions. First, all possible outcomes are known in advance. Second, the exact outcome cannot be predicted. Tossing a coin, we know the menu, heads or tails, but we can't predict which. Both boxes ticked. Random experiment. Boiling water, we know exactly what happens. It evaporates at 100 degrees. Predictable. Not a random experiment. Let's drill it. Rolling a dive, random. Dropping a stone, deterministic, it falls guaranteed. Tomorrow's stock price, site and random. Whether a user clicks your AD7, random, and notice that last one is exactly what ad companies model with this machinery. The two-part test: outcomes known, result unpredictable. Word 2 of our vocabulary, the sample space, written as capital S. The sample space is simply the set or all possible outcomes of an experiment. The complete menu. Toss one coin, S is heads, tails, 2 outcomes. Roll a die 1 through 6, 6 outcomes. Now toss 2 coins, and here's where beginners stumble. The sample space is heads, 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 tails, tails, heads, and tails, tails. 4 outcomes, not 3. Heads, tails, and tails, heads are different outcomes. First coin versus second coin. Miss that and every probability you compute afterwards is wrong. This exact confusion is why people think one head in 2 tosses has probability 1/3. It's actually 2 out of 4, 1/2. An event is any subset of the sample space, like at least one head, and in machine learning, an email classifies sample space as spam, not spam. A digit recognizes 0 through 9. A language model choosing its next word. A sample space of 50,000 outcomes, every single word position. Same concept, bigger menu. Now for the concept the whole chapter is named after, the random variable. And I'll be honest, the name is misleading. It's not really a variable, it's a function. A random variable assigns a numerical value to each outcome of a random experiment. We write them as capital letters X, Y. Our running example, toss 2 coins. The sample space heads heads, heads tails, tails heads, tails tails. Define X as the NUMBR of heads. Then X maps, heads heads to 2 heads tails to 1 tails heads to 1 tails tails to 0. Why bother converting outcomes to numbers? Because you can't do math on the word heads. You can't average heads and tails. But once outcomes become numbers, you can average them. The expected number of heads is one you can measure spread. You can build distributions. The random variable is the bridge from raw outcomes to the entire toolkit of mathematics. Every neural network output is a random variable. For exactly this reason, numbers are computable. Random variables come in two species, and telling them apart takes one question: can you list the possible values? If yes, finite or countable, it's a discrete random variable. Number of heads in 2 tosses 0 1 2. Listed. Dice scores emails per hour. Defective items in a batch, all discrete. If the variable can take a and y value in an interval, it's continuous. Height of students anywhere between 4 and 6 feet, including 5.731. You cannot list them. Temperature, weight, waiting time continuous. The species determines the tool. Discrete variables get a probability mass function, continuous ones get a probability density function. And one mind bender for the road: for a continuous variable, the probability of hitting exactly 5 feet infinitely precisely is 0. Probability lives on intervals, like between 4.9 and 5.1. Quick round: students absent today discrete. Rainfall in millimeters, continuous. Goals in a match dive discrete. Battery life in continuous. You've got it? Now we can define the star object of this chapter, the probability distribution. A distribution assigns a probability to each value of the random variable. For our 2-coin experiment with X, the number of heads, look at the table on the right. X equals 0 probability 1/4, only tails tails. X equals 1 2/4 because both heads tails and tails heads deliver 1 head. X equals 2 1/4. For a discrete variable, this table is called the probability mass function, the PMF. Every legitimate PMF obeys 2 laws. Every probability is at least 0, and they all sum to exactly 1. Check ours: 1/4 plus 2/4 plus 1/4 1. Valid. And here's the deep learning payoff in the green box. When a classifier's softmax layer outputs cat 0.7, dog 0.2, bird 0.1 non-negative, summing to 1, that is a probability mass function. Every classification network on Earth ends by manufacturing exactly the object on this slide. Time to meet the first famous distribution, the binomial. It answers one specific question in a fixed number or yes or no trials: how many successes will I get? It's built on Bernoulli trials, independent little experiments with identical chances, and it applies when 4 conditions hold. Let me give them to you as a checklist. 1. A fixed number of trials, say 10 coin flips, decided in advance. 2. Each trial has exactly 2 outcomes, success or failure. 3. The trials are independent, one result doesn't influence another. 4. The probability of success is constant, a fair coin stays 50-50 on every flip. The checklist matters most when it breaks. Drawing cards without replacement. Each draw changes the deck, independence and constant probability both violated, not binomial. Flipping until the first head appeared. The number of trials isn't fixed, not binomial either. Coin flips, defect counts in a batch or 100 survey predictions, free throws, that's binomial territory. Memorize the 4 fixed n, 2 outcomes, independent, constant p. Here's the binomial formula, and rather than memorizing it blindly, let's understand why it must look this way. Probability of exactly r successes equals, and choose r times p to the r times 1 minus p to the n minus r. Read it as 2 questions. Question 1: what's the probability of one particular arrangement of r successes and n minus r failures? Multiply the chances p to the r times 1 minus p to the rest. Question 2: how many arrangements are there? And choose r ways to pick which trials succeed. Multiply the 2 answers. Done. The formula assembled itself. Worked example: fair coin, 3 flips, exactly 2 heads. 3 choose 2 is 3. Half squared times half is 1/8. 3 times 1/8 0.375. Don't trust me, verify by brute force. List all 8 sequences of 3 flips, which have exactly 2 heads. Heads, heads, tails, heads, tails, heads, tails, heads, heads. 3 out of 8. Same answer, 2 roads. That's how you know a formula. Bonus gifts for the exam. The mean is n times p, and the variance is np times 1 minus p. Our second famous distribution, the Poisson. Different question this time, no fixed number of trials at all. Instead, events arrive randomly over an interval. How many will arrive? Emails per hour, calls at a call center, accidents per month on a highway, typos per page, server requests per second. Count events in a fixed window. The Poisson has exactly one parameter, lambda, the average rate. If you receive on average 5 emails per hour, lambda is 5, and the formula tells you the probability of exactly 0 emails, exactly 3, exactly 10. It's checklist. We count events over a fixed interval, and the interval can be time, area, or volume, like floors per square meter of fabric, at a constant average rate. With independence, what happens now doesn't affect what happens later. 2 elegant facts to finish. For the Poisson, the mean and the variance are BOTH, lambda its signature. And the deep connection, Poisson is what the binomial becomes when n grows huge and p shrinks tiny. Rare events, many opportunities, that's Poisson country. We now have 3 flavors of probability to master, and they form the grammar of all probabilistic reasoning. Flavor 1, marginal probability. Marginal probability is the probability of one event ignoring everything else that might be going on. It answers, what's the chance of this one thing, no matter what else happens. Simplest example on earth, pull a card from a deck, probability it's red, 26 red cards out of 50 to 1/2. Notice what we did, we ignored rank, suit, everything except color. That act of ignoring is what makes it marginal. Where's the funny name from? Picture a joint probability table, rows for one variable, columns for another. Sum each row and write the totals in the margin of the page. Those margin numbers are the marginal probabilities. The name is literal. The formula on the slide says the same thing. To forget variable b, sum over everything b could possibly be. Discrete case, sum. Continuous case, integrate. Same idea. Let's make marginal probability mechanical. 3 steps, then a worked problem. Step 1, identify the joint distribution, the full table over both variables. Step 2, eliminate the variable you don't care about, sum if discrete, integrate if continuous. Step 3, interpret what's left as the probability of your single variable. The problem on the slide, 2 fair dice are rolled. What's the probability? The first die shows 3. Pictured 6 by 6 grid, all 36 outcomes, each with probability 1 over 36. The event first die equals 3 is one entire arrow. Blew off that grid. 3 1 3 2 3 3 3 4 3 5 3 6 6 cells, 6 over 36 1/6. See what we really did? We summed across all 6 values of the second die. Marginalization in action disguised as counting a row. Try the mirror image yourself. Probability, the second die shows 5. Same logic, 1 full column, also 1/6. Flavor 2 and this one is where probability starts feeling like detective work. Conditional probability, the probability of an event given that another event has already occurred. The notation, P of A, vertical bar, B. Read it, probability of A, given B. The formula, probability of A and B together, divided by the probability of B. But here's the intuition, and it's the best mental picture in this chapter. Conditioning shrinks the universe. When someone tells you B happened, you throw away every world where B didn't happen, and remeasure your event inside what remains. The division by P of B is just rescaling, so the shrunken universe's probabilities total 1 again. Watch it work. Roll a die, probability of a 6 1 and 6. Now I whisper, the roll was EVN. Your universe shrinks to 3 worlds, 2 4 6. Probability of 6 given even 1 in 3. Information changed the probability. That single idea, updating on knowledge, is the seed that grows into Bayes' rule a few slides from now. Here's the 5-step recipe for any conditional probability problem plus an example with a twist ending. Identify the 2 events. Find P of A, find P of B, find the joint P of A and B, then divide. The example, toss 2 coins. Event A head on the first coin. Event B head on the second. What's the probability of B given A? The joint both heads is 1/4. P of A is 1/2. Divide, 1/4 over 1/2 1/2. But wait, 1/2 is just P of B on its own. Knowing the first coin landed heads told us nothing about the second. And that right there is the formal definition of independence. P of B given A equals plane P of B. For contrast, draw 2 cards without replacement. Probability the second is an ace given the first was 3 in 51 changed. Dependent? Coins don't remember, decks do. Let's put all 3 flavors side by side, because exam questions love to blur them. Marginal P of A alone. One event, everything else ignored. Probability of a red card, 26 over 52. Joint P of A and B, 2 or more events happening simultaneously. Probability of red and king 2 cards, 2 over 52. Conditional P of A given B, probability or one event knowing another occurred. Probability it's a king given it's a face card, 4 kings among 12 face cards, 1/3. And notice the beautiful relationship binding the family. Joint equals conditional times marginal. P of A and B equals P of A given B times P of B. Rearrange that innocent equation and, next slide, Bayes' rule falls out. Instant drill rain A and D traffic joint. Traffic GIV and rain conditional. Rain full stop marginal. Got it? Good. Now we compress an entire distribution into single summary numbers. Number 1, the expectation, the long run average. The expected value is what you'd get on average if you repeated the experiment many, many times. The recipe, weight each value by its probability, and sum. It's a weighted average where probability does the weighting. The classic affair die, 1 through 6, each with probability 1/6. Expectation 3.5. Now pause, 3.5. No face of any die shows 3.5, and that's an important lesson. The expectation need not be a possible value. It's the long-run average. Roll 600 times, your mean hovers near 3.5. Where this bites in real-life, casinos and lotteries run entirely on expectation. A ticket costs 100 rupees, weighted winnings 45. Play forever, lose 55 per ticket forever. The casino doesn't gamble, it collects an expectation. And in deep learning, the loss we minimize is an expected loss over the data distribution. This little concept sits inside every training run. Summary number 2, variance. How spread out are the values? 2 archers can both average a bullseye while being completely different archers. Archer A's arrows land within 2 centimeters of center, low variance. Archer B's arrows scatter across the whole target, high variance. Same mean, utterly different reliability. That missing information is what variance captures. The recipe in 4 moves: find the mean, subtract it from each value, measure the deviations, square the deviations, average the squares. Why square? 2 reasons. First, raw deviations always sum to 0, positives cancel negatives, telling you nothing. Second, squaring punishes big deviations extra hard. 1 wild arrow matters more than 3 slightly off ones. Low variance values hug the mean. High variance values scatter widely. 1 practical cousin, the standard deviation, just the square root of variance, which conveniently lives in the same units as your data. And 1 exam warning: read carefully whether the question wants variance or standard deviation. They differ by exactly that square root. Variance describes 1 variable spread. The moment you have 2 variables, a new question appears: do they move together? Enter covariance. Covariance measures the relationship between 2 random variables, the extent to which they change together. Positive covariance: as one rises, the other tends to rise. Height and weight. Study hours and marks. Temperature and ice cream sales. Negative covariance: one rises, the other falls. Price and demand. Altitude and oxygen. Absences and grades. Near zero, no linear relationship. Shoe size and marks. Our old friends. The formula reads, the expected product of the 2 deviations. When x and y sit above their means together, the products come out positive. That's togetherness measured. 2 cautions before the worked example. The raw number is scale dependent, measure in centimeters instead of meters, and it changes, so trust the sign, not the size. And the big one, covariance is not causation. Ice cream sales and drownings covery, because of summer, not because of each other. Let's compute a covariance and 2 and, with real numbers. This exact calculation is an exam staple. The data, 5 students. Hours studied 1, 2, 3, 4, 5. Test scores 60, 70, 75, 85, 90. Step 1, the means hours average 3, scores average 76. Step 2, deviation products, student by student. Take student 1 hours deviation 1 minus 3, minus 2. Score deviation, 60 minus 76, minus 16. Product, minus 2 times minus 16 plus 32. Below average hours, below average score. The directions agree, so the product votes positive. Feel how the formula thinks. Step 3, all 5 products sum to 85. Divide by n-14 and the covariance is plus 21.25. Conclusion positive. More study hours go with higher scores. As for the number 21.25 itself, scale dependent, remember the sign is the story. And a connection to smile at. This exact computation is what fills the covariance matrix inside PCA Part 1 and Part 2 of our unit. Just shook hands. And now the most famous formula in this entire chapter, Bayes' rule, the mathematics of changing your mind. Bayes' rule tells us how to update a probability when new evidence arrives. The formula, P of A given B, equals P of B given A times P of A divided by P of B. But the formula only comes alive with its vocabulary, so here are the 4 names. P of A, the PRIOR, your belief before evidence. P of B given A, the likelihood, how probable this evidence would be if A were true. P of A given B, the posterior, your updated belief. And P of B, the total probability of the evidence. Prior in, evidence weighed, posterior out. It's a belief updating machine. You met a Bayes machine today, by the way. Your spam filter is literally called Naive Bayes. Prior, how common spam is overall. Evidence, the email contains free, with 3 exclamation marks. Posterior, probability of spam given that word, email moved to junk. Where does the formula come from? 2 lines. Write the joint probability both ways. P of A given B times P of B equals P of B given A times P of A and divide. That's the whole derivation. Next slide. Bayes destroys everyone's intuition. This might be the most important slide of the unit for your real life. The medical test paradox. Set up a disease affects 1% of the population. The test detects it 99% of the time, with a 5% false alarm rate on healthy people. You test positive? How worried should you be? Your gut screams 99% sure I'm sick. Bayes disagrees. Watch. Forget formulas, let's just count people. Take 10,000. 1% are sick, 100 people. The test catches 99 of them, 99 true positives. The other 9,900 are healthy, but 5% false alarm on them means 495 false positives. Now you're one of the positives. Which kind? 99 true, 495 false. Probability you're actually sick, 99 out of 594, about 17%. Not 99, 17. The rarity of the disease means false alarms swamp true detections. This error, ignoring the base rate, is made by real doctors interpreting real tests. You now know better, and if a second independent test also comes back positive, run Bayes again, with 17% as your new prior. Belief updating, chained. Last stop in this chapter, information theory, the mathematics of surprise. Invented, incredibly, by one person, Claude Shannon, in 1948. The guiding intuition, learning that an unlikely event happened is more informative than learning a likely one did. The sun rose this morning, probability 10, information, don't bother tweeting it. A solar eclipse this morning, rare, highly informative. Shannon turned that into a formula. Self-information, I of x equals negative log of p of x. Small probability, big log magnitude, big surprise measured in bits. Then entropy, the average surprise of a whole distribution, its overall unpredictability. 2 quick computations. A fair coin, entropy exactly 1 bit, maximum uncertainty for 2 outcomes. A 2-headed coin, entropy 0, the outcome is certain, so revealing it tells you nothing. Uniform distributions maximize entropy, certainty zeros it. Hold this thought tight because the next slide connects it directly to how every classifier on Earth is trained. Here's the information theory toolkit and the payoff I promised, the bridge from Shannon to your loss function. Tool 1, self-information, the surprise of a single event. Negative log p. Tool 2, entropy, the average surprise of a distribution. Uniform means maximal, certain means 0. Tool 3. The star CROSS entropy. It measures how badly a distribution Q. Your model S prediction describes the true distribution P and its companion, KL divergence, the wasted bits, the distance between the two distributions. Now the punchline. When you train a classifier with cross-entropy loss, the default in every framework, here is literally what happens. The truth says cat 100%. Your model says cat 70%. The loss is negative log or 0.7, about 0.36, the surprise the model assigned to the truth. Perfect prediction, log or 1, loss 0. Confidently WRONG cat at 1%. Negative log or 0.014.6. The loss explodes. Cross entropy punishes confident mistakes brutally, and now you know exactly why. Shannon 1948, hiding inside every model. Fit 2026. Quiz 4. The Bayes test. And I'll warn you, intuition fails most people here. Let's see about you. A disease affects 1% of population. A test detects it 99% of the time, with a 5% false positive rate. A random person tests positive. The probability they actually HIV the disease is closest to A 99%, B 95%, C 50%, or D 17%. My advice: don't reach for the formula. Count people, 10,000 of them. How many are sick? How many positives are true? How many are false alarms? Pause the video and count it out. The answer is D, 17%. If you answered 99%, welcome to the majority of humanity, including, in real studies, many practicing doctors. Let's redo the count. 10,000 people, 100 are sick, the test catches 99 true positives. 9,900 are healthy, 5% false alarms gives 495 false positives. So the positives number 594, and only 99 of them are genuinely sick. 99 over 594, 17%. The lesson burned in the test's accuracy is not your probability of being sick. The base rate that the disease is rare dominates everything, because rarity mass produces false alarms. Homework: if you dare, rerun the count with a disease rate of 0.1%. The answer collapses to about 2%. The rarer the disease, the less a single positive test means. That's base rate neglect, and you are now permanently vaccinated against it. If this lecture helped you, do like, share and subscribe to Shri Tech Bytes for more lectures like this one. See you in the next video.